All right, here at Chapter 5, we're switching gears a little bit, moving towards working with functions that have exponents. We won't see these till later in the unit, but we'll get to logarithms. If you've seen these topics before, you know they very naturally fit together because they're inverses. But right now we're focusing on exponents, and in particular we'll look at integral exponents, which is really nothing more than a nice little fancy way of saying we're looking at exponents that have whole numbers. Just a few basic laws here to take a peek at. If we have two exponential expressions that have the same base, those can be combined into a single exponential expression by adding the exponents. Okay, that can be a little bit tricky to remember that when we're multiplying the two terms, we add the exponents. Likewise, if we're dividing, we could subtract the exponents. Okay? Two expressions, if they have the same base, will only equal each other if their exponents are exactly the same. Okay, that would not necessarily be true for bases that are 0, 1, or -1. Okay? Right now, we'll keep running through some of these laws, and then we'll get to some examples. If we have a term that is a product of a times b, we can take our exponent x and apply it to each component of that product individually. Likewise, if we're dividing a divided by b and raising that whole term to the x power, we could apply the exponent to each term individually. If we have a situation like this, where we have b to the x power and that whole quantity raised to the y power, we could multiply those two exponents. Okay, and then lastly, a couple miscellaneous laws. Anything to the 0 power is 1. And if we have a negative exponent, we could write that reciprocal as 1 over b to the positive n. All right, some examples. Okay. X to the 4th times x to the 3rd. First thing to notice here is they have the same base. Because of that, we can add the exponents here, and that would be x to the 7th. Okay. Easy way to kind of justify that law really quick here. I'm actually going to just get some space by going up top. If we wanted to write out x to the 4th, that's x times x times x times x. Okay. That is being multiplied by x to the 3rd, which is x times x times x. And to get a final answer here as to how many times we're multiplying x, just count them all up, and you'll see there's 7. Okay, really just a natural way to look at that law and see that, in a really simple manner. It makes a lot of sense, and even though it's not necessarily the most logical thing that when you're multiplying the two terms you add the exponents, that when you break it down that way, that is what makes sense to be done. 4 to the negative 2nd we could write as 1 over 4 to the 2nd, or 1 over 16. Same thing on this problem. We could go 1 over negative 3 to the 4th power, which we could continue to simplify as negative 3 to the 4th is 81. We could rewrite that as 1 over 81. Three times, again, the way we can always get rid of that negative exponent is to flip that and put it down in the bottom of that fraction. 2 to the 6th power would still be down on the bottom, and we could do 3 over 2 to the 6th, okay, which would come out to be, let's see here, 2 times 2 times 2 times 2. There's let's see here. Here we'd have 4 times 2 is 8, times 2 is 16, times 2 is 32. That would fully simplify to 3 over 64. Okay. Last example. Here's one where we have the product. We have 5 times x to the second. So this negative 3 will apply to the 5 as an exponent. And it would apply to the x, which we could multiply 2 by negative 3. Both of those exponents turn negative, which means we could make them positive by going 1 over 5 to the third and x to the sixth. 5 to the third power is 125. Fully simplified answer would be 1 over 125 times x to the sixth power. A couple more to try here. First thing I would do on this one right here, and if you'd like to, I mean, if these were problems in class, what we would do at this point is just kind of pause and give everybody in class a chance to work through these on their own to try to do them independently. If you'd like, this would be a great time to pause. You could certainly do that and kind of see how it goes. What I would do on this one here is rewrite that as 1 over 4. This could be rewritten as 1 over 2. Then we can get a common denominator here. Subtract those, which would end up being negative 1/4 squared, which would be negative 1/4 times negative 1/4, which would simplify all the way to 1 over 16. Okay? Here what I'll do is multiply this negative 1 and apply it to each of these terms. I do want to make a point to state here that didn't work on this example because these two terms were not being multiplied. Okay, we had that property that we're looking at right here, that if we have a times b to the x, that we can take this exponent outside the parentheses and apply it to each part of the product. On the second example, that works because m and n, those two terms, are being multiplied. Here in the first one, they weren't. They were being subtracted. Okay, so that law that I'm going to use in the second example does not apply at all to the first one. We'd end up having, after we multiply m to the first times n to the second, and I suppose to be fully simplified, we wouldn't have to write the first power. We could just say m times n to the second. Okay, and that would really be all for that. I look at a couple growth and decay models here, just to kind of label some parameters. If we have y equals a times b to the x power, a is always going to end up being your starting amount. B is your growth rate. Keep in mind here, if we ever see that b is bigger than 1, that would be an exponential growth problem. If it's ever between 0 and 1, that's a red flag that it's a decay model. Okay, x usually represents time. Okay, it's important to note here that that's a variable, and we treat it as such. We can put different values in there. Y is your ending amount. It's also a variable, but this is the dependent variable. Okay, that value for y depends on what value was chosen for x. Quick example here that says that plane tickets in 2000 on average were $250 and have increased by 14% per year, right? The exponential function that models that data. Well, we're going to put it in the form of y equals a times b to the x. Okay, y is a variable, so I will leave it at that. 250 is the starting amount, and here's what we have to do for the growth rate. Okay, number one, as just about always when we do any type of operations that involve a percent, it needs to get switched to a decimal. So we should be working with 0.14, not 14%. However, I do want this model to represent growth, so each year I want it to take 14% of the previous year and add it on to that total. To do that, for my growth rate, I will use 1.14, and that will make sure each year that we include the price of the ticket the previous year and then add on 14%. Okay? For part B, to get the average cost in 2012, what I'm going to do here is just make sure it's clear that let X be the number of years after the year 2000. Okay, for example, I'm not gonna plug in 2012 here. Instead, I'm going to say 250 times 1.14. I'm just going to raise it to the 12th power because the way I've set this up, if I put in x equals 0, anything to the 0 power would be 1, and I'd just be left over with the starting amount. Okay, so here I would evaluate at x equals 12. Whatever I get, you go ahead and crunch those numbers. I think it ends up being over 1,000, just as far as kind of a ballpark for what you should be expecting. And here's a depreciation. Okay, now we said here that what we should be looking for in a model that has exponential decay is a growth rate that's less than 1. Okay. Now, it says the value of the car is going down 6.5%, so I should use 0.065, all right? But that's going down from the value of the previous year. So each year it's losing 6.5%. All right, so I'm still going to add this, include 1 because I want to base this off of the previous year's price. Brand new, it's $35,000. But instead of adding, now I'm going to subtract, okay, to make sure that each time I evaluate at x, it loses 6.5% to whatever its value was the previous year. Once I have it set up this way, make sure that's in parentheses because on this we'd likely use a calculator. Once again, I could just evaluate at 10. Whatever I get for that y value is going to be the value of that car after 10 years. Okay, it should be significantly less than $35,000. Okay, so there is an example with exponential decay, and if I were to simplify this, because this would technically be the value for b, my rate, okay, that would come out to be 0.935. Okay, so that value, like we saw earlier, is less than 1, which is consistent that this is a depreciation or a exponential decay model. Year after year, our amount, which starts at $35,000, is going to be going down. Okay, that's all for 5.1. What you're going to see in 5.2 is some more properties of exponents, but we're going to switch gears a little bit and look at rational exponents, which is, again, just a fancy way of saying now we'll look at some problems that have fractions in the exponents, not just whole numbers.